Hey guys, I'm going to walk you through the first problem on the chi-square practice problem sheet. Just if you're having some problems trying to word this or figure out what numbers go where, I'm going to show you. So here's the problem. We have 433 grains of this corn, and it gives us some numbers of what we had when we counted them. And our tentative hypothesis, and in other words, we would call that our experimental hypothesis, is that we think that these parents are heterozygous for both traits. And if they are heterozygous for both traits, then their offspring should be in a 9:3 to 3:1 ratio. So our question is what we found in a 9:3 to 3:1 ratio to support our hypothesis? So the first thing when you're doing a statistical analysis is we work off of the null. So our null in this case is that there is going to be no statistically significant difference between our observed and what we expected. Meaning that if they're close enough, if we accept our null hypothesis, it supports our experimental hypothesis. If we reject our null hypothesis, that means that the offspring is not following the 9:3 to 3:1 ratio that we were expecting. And so we cannot say that our hypothesis that their parents are heterozygous for both traits. The first thing to do this, we have to do a chi-square because, right, these numbers don't mean a whole lot to us. I mean, we can eyeball and be like, I don't know, it kind of looks like 9:3 to 3:1 because it's getting lower, but we don't know for sure. So the chi-square analysis is helping us to be more precise when we're looking at numbers. So our observed, that's the first thing you need to look at. That's always the information you found, the data that you got when you did the experiment. So we observed, they told us that we observed 271 purple and starchy, 73 purple and sweet, 63 yellow and starchy, and 26 yellow and sweet. So how do we find our expected? Well, we expect them to be in a 9:3 to 3:1 ratio. So we need to find, out of this population of 433, what, if it was 9:3 to 3:1, what would that translate into numbers out of 433? So you take the total number, change my color. 433 is our total, our population that we're looking at. And if we are going to try and find 9/16 of that, and how did I know 16? Because this adds up to 16, so it's out of 16 different options. We just multiply it by 9/16. That means 9/16 out of 433. We do that for all of them. This should be a 3/16. The last one is 1/16. Notice my 9:3 to 3:1. And this should all add up to, because it should be 100%, 16 out of 16, it should also add up to 433. That is a way to check that you are doing your expected correctly. So you plug this into a calculator, and I'm just going to pretend I'm plugging it into a calculator, but I already have it. This is going to come out to 243.56. This one comes out to 81.19. This is the same. And this last one comes out to 27.10. Notice that I'm rounding to decimal places. It's important to not round to the whole number because it will make too big of a difference on your chi-square value that you get. Another thing that I want you to notice is that I'm multiplying it out of the total number. A lot of students multiply it out of the observed, so they would put 271 times 9/16. That means that you're finding 9/16 of that. And we want to find 9/16 out of the whole population, which is that. So don't mess up there. Now we just plug it into our equation, which, if you remember, I'm going to write it up here. Can you see that? Chi-square is the summation of the observed minus the expected squared over the expected. So we always break this down into parts. I'm just going to do it all at one time to get our number. So I'll do the first one with you, and then I'll just write the numbers for the rest. So for the first one, our observed is 271 minus our expected 0.6, square that, and then divide it all by our expected. And you get, when you do that, plug it into the calculator, you get 3.09. So if I follow that same equation, I do it for all 4 of these, the second one will come out to 0.83, the third one will come out to 4.08, and the last one will come out to 0.04. Now the last step that we missed is we didn't do this summation of. All we did was this equation. So now we need to add them all up. When you add them all up, we get 8.04. That is our chi-square value. Now this chi-square value, it doesn't really mean a whole lot to us. It's not significant until you use it in the table. So the next thing that you need to figure out is what is our degree of freedom? Our degree of freedom is how many events there are, outcomes there can be, minus 1. So it's 4 minus 1 equals 3. And what we're trying to do is, when we look at this table, and Leslie, I'm using your paper, we are working here. There's our degree of freedom, so we're in this row. If it was 2 degrees of freedom, we'd be looking here. And this is our critical value. Why is it our critical value? Because we want to see where we are in relation to the p-value. This p-value is 0.05, and as you can see this line right here, if it's less than 0.05 or the same, we are rejecting our null. If it's greater than 0.05, then we are accepting our null. Notice how the the p-values get smaller going in this direction, larger in this direction. So our chi-square is 8.04. On this table, that is greater than our critical value, which is 7.82. So we know that where we fit, our p-value is less than 0.05, right here. But our chi-square value is greater than the critical value. So we're here. So what does that mean? Well, it tells us here that's a poor fit, but we know from our other table that that means to reject the null. So how do we write this out into a CER format? Well, we're rejecting the null. So our claim, let's look back at what we said at the beginning. Our claim is that if we reject, it does not follow a 9:3 to 3:1 ratio. So our claim is the parents are not heterozygous for both traits. What is my evidence for that? My evidence is that our p-value is less than 0.05, and we reject the null hypothesis. There is a statistically significant difference between the observed data and expected data. So that's basically therefore. So what does that mean for us? Because of this difference, we cannot say that the observed offspring are following a 9 to 3 to 3 to 1 ratio that would be present if the parents were heterozygous for both traits. So notice when I'm writing my CER, my answer, there's my claim in the first sentence. My evidence is talking about our chi-square and how it rejected the null. And then we have to explain what that means for our actual experimental hypothesis. Because we rejected the null, what does that mean for what we were trying to figure out? And that's the answer. That's all you have to do. So I hope this helped you guys.